So yeah, in an optimal world, there would be someone here at the board that actually knows anything about additive combinatorics. This is not the case, but I will still tell you about a little bit about additive combinatorics, because what I want to talk about is sort of non-abelian additive combinatorics, maybe multiplicative combinatorics. So here is what my view of what additive combinatorics is. So suppose A is a set of numbers or a set of elements in an abelian group. Then you can add A to itself. Namely, you can look at all A plus B's where both A and B come from A, and just look at how large this set is. Potentially, this can be the size of A squared. So something special must happen if instead of A squared you get just K times A for K, which is not so large. So here's a typical question in additive combinatorics. So suppose A plus A is small. Can you say that A has some structure? So that's more or less a typical question. And here is, and the answer is yes, you can say things. So here is first Z then S. So here's an example of something that you can say. If A is in, I'm not saying it in the maximal generality, but say it's in Zm to the n, and it satisfies this, then you can say that A is covered by at most 2 to the poly k cosets of some subgroup H that is whose size is somehow related to the size of A. So I mean, a typical case where A plus A is actually equal to A would be where A is actually a subgroup. So this Ruja result says that it's in some sense close to a subgroup. This type of results is called Feynman-Ruja, because Ruja proved this and Feynman proved something similar earlier, I think, for the integers. There was a conjecture called the polynomial Feynman-Ruja conjecture, which says that this can actually be made polynomial in K instead of exponential in K, and this is now known to be true, more or less. This is a result by Gowers, Green, Manners, and Tau. Very new. So this is the polynomial Feynman-Ruja.
And with the M?
Manner.
Freddie Manner.
Yeah, so quite exciting, and it maybe surprisingly, or maybe not, this actually has applications in computer science, for example, for pseudo-random generators, but also for other things, testing. So this is, was open for a long time. Here's another thing that you can say that at least qualitatively is stronger. So this is Bogolyubov-type 39, and the best so far is by Sanders, from 2012. Sanders. Yes. It can be phrased in using this K, but I will say it in a different way, which is more suits my needs. So if I have a set A in FQ to the N, the reason I change from Zn to FQ is because I'm going to use FQ, but actually this can be Z to the M. And suppose that the measure of A is alpha. Measure of A is just the size of A divided by the size of this. And then I don't assume anything about A plus A. I just say that A, if you look at A minus A and add it to itself, of course this is abelian, so that's actually just 2A minus 2A. But anyway, this, knowing nothing about A, I can say that it contains a subgroup. So now it doesn't, there are no like shifts of a subgroup. It actually contains one subgroup, V. And the subgroup is not too small, so the measure of the subgroup is quasi-polynomial in the measure of A. Another way, more concrete to say it is that the codimension of this subgroup, you can consider, you can think of it as a linear space. The codimension is going to be some constant that depends on Q times log 1 over alpha, but the log is to the 4th power, so the size is going to be still not polynomially small in the size of A, but only quasi-polynomially small. Right. This is also conjecture to hold with a polynomial term in mu of alpha. This is still unknown as far as I know. Okay, and what we want to do is prove something like this, where the mu of V is actually polynomial, but not in the abelian setting. So let me tell you what setting I want to talk about. So I think of Q as some large but constant prime. You're allowed to think of it as a prime power. That also works, but it doesn't play a lot of any significant part. And I think of N as something that is asymptotically large, and we consider a similar question for subsets of the group SL N of FQ, and just to save on chalk, I will just write SLNQ from now on. So maybe I will say what this is. So here is a SLNQ. It is actually contained in a GLNQ, which maybe you know better, and that is actually contained that is a set of n by n matrices with entries in FQ. So this is an abelian group. You can just add matrices, that's easy. This is a multiplicative group. This is the set of invertible matrices, so you can multiply and you can also divide. So that's a multiplicative group, which is non-abelian, and this is just the set of invertible matrices where the determinant is 1. Actually, anything that I say will work both for SLN and for GLN. Sometimes GLN is a little bit more annoying to work with. Some SLN also has its annoyances. It's just a matter of convenience. And just to get a quantitative feeling, so here a matrix has n by n, so n squared coefficients. So the size of this sim is roughly q to the n squared. When q is large, basically all matrices are invertible. So this is still q to the n squared, maybe divided by 4 if q is 2. Much better for larger q's. And the determinant can be anything, these are invertible matrices, so anything between 1 and q minus 1. Here we want it to be 1, so you need to divide by q minus 1. Still, compared to this, it's basically all q to the n squared. This is the amount to the expression to remember. And our main result for today is that for some positive constant, you can say that for any subset of SL and Q, A minus A plus A minus A, but in a product form, contains a subgroup G and the size of G is at least the size of A to some power C, so C is constant, and therefore the size of G is at least polynomial in the size of A, and that's why we call it a polynomial Bogolyubov result. So, and it's non-abelian. Also explain some of the names. And actually I can tell you how this subgroup looks like, which I will actually do. So, okay, I need to do the squeegee thing, so you can think how this subgroup looks. It actually looks just like SLNQ with a smaller dimension. So how do I find a smaller SLNQ? So SLMQ inside SLNQ. Just wait until I finish this squeegee thing. So here's a set, LK, K is a parameter. It's going to be all the matrices that have a K by K block. It's just the identity, 0 here, 0 here, and any X that you want here, as long as X is an SL n minus K over ZQ. So these matrices are invertible. Their determinant is 1 because the determinant of X is 1, and of course this is determinant 1. When you multiply two such matrices, they remain of this form. So this is actually a subgroup. I cannot say that G must be of this form, but I can say that G is joint to this form. So if I have this definition, then I can say that moreover, G can be taken to have the form psi LK psi minus 1 for some psi in SLN Q. So this subgroup must be similar to LK, and LK is just SLN but with a smaller n. So I'm very concrete about what subgroups this A minus A squared must contain. I have a name for such subgroups. This is called I think Noam picked the name, so don't blame me. It's called a good 2K Triumvirate. So why? Because this says that G is a group. Umvirat means that it's an umvirat. So why do I, actually it's a 2K umvirat, because there's another way that I could define this LK. LK is the set of all matrices that send the first K unit vectors to themselves. So that's K constraints. And also if you multiply vectors from the left-hand side of the matrix, it also sends the first K vectors to themselves. So that's 2K constraints, that's why 2K and umvirect. Actually, since we're at it, I can say that...
why is it good?
Oh. I think it's good. Yeah, so it's good because we have another thing that's not called good, which I don't think I will get to.
What is an umvirat?
Sorry?
Umvirat.
Oh, yeah, so if you have it's sort of like a junta, right? A triumvirate is something that is governed by 3 people. So this is governed by 2K vectors, like E1 to EK and E1 to EK transpose, right? So if they are sent to where they are supposed to be sent, then you are in LK. And the same is also for G, but for just other vectors. Right, so that's a reason for the umvirat part. Yeah, and actually, if we look at something like psi L and, I don't know, psi to the minus 1, so this is not a subgroup, but it is still a good 2K umvirat. Okay, no, not a group. Sorry?
What is psi?
Anything, some matrix, some invertible determinant 1 matrix. So it's a change of basis. So it means that if you look at one, there are 2 bases in which you look at the set of matrices that look like this in this basis, set of transformations that look like this in this basis. Okay. Questions? More? Okay. let's say something about the proof. So a very important notion for the proof is the notion of a global set. So we are talking about subsets of L and Q, and I want to tell you when a set is global. So maybe I'll tell you what set is the most not global that you can think of. Lk is not global. It's not global because it has a huge correlation with a subgroup or with an umvirat. And being not global, and being global means having little correlation with such structured sets. So you can think of global sets as being pseudo-random with respect to the group structure. So A in S and Q N is R global. So there is a parameter if its relative density inside a K umvirate. So I didn't define, there are several things that I didn't define here, but K umvirate, just think of 2K, a good 2K umvirate, that's enough for our needs. So that its relative density inside the K umvirate is not much larger than its original density. So it's spread evenly. So is at most R to the K times the overall density of A. So K umvirate, just think of 2K umvirate. So a subgroup or a coset of a subgroup, a double coset of a subgroup.
That's inside every K umvirate.
Any, yeah. Yeah, sorry. So inside any coset of a subgroup of codimension K, the relative density, which is what you would expect, the size of A inside this over the size of the subgroup or the coset. So this is not bigger than mu of A by more than R to the K. And I will get rid of this R, and I will say that it is just global if it is Q and there will be a constant here, global, and here there's a constant. This is my best impression of zeta, but this is some constant. Why does this constant make sense? Because in one umvirate, for example, I demand that one vector goes to one other vector, right? So this is n linear constraints. This is a constraint on one column of the matrix. So every one umvirate reduces the size of the set that I'm looking for by a factor of q to the n. And this says that if you look at subsets of which have a nice structure and density q to the k times n, then the density inside them of A is not going to be greater than some polynomial in how small the set is. Okay. And let me tell you why this global is so important. I'll just cheat. So I don't clear clean, I smear, yes.
I just wanted to ask about the constant zeta. So on what does it depend? Is it
It's a
random?
constant
Does it
for
depend
which
on
the
Q?
proof works.
But does it depend on Q or?
That's a good question. I mean, it's by what I said so far, it's allowed to depend on Q. I think it doesn't depend on Q, but I'm not totally sure.
Okay.
Because we just say, in the paper we just say it's going to be constant, and whenever we have some constraint on it, it's always a constraint that says that it has to be larger than something, and smaller than something, and yeah.
Okay, I think I got a little confused. All the definitions on the board involve goodness. What is just a plain K umvirate?
Yeah, so good means that you have the same number of constraints from both sides of the matrix.
So what is just a plain K umvirate? Could you say that one more time?
I didn't want to say, but okay. So it just pick K vectors, but some of them are vectors, and some of them are column vectors, and some of them are row vector, and look at the set of matrices in SLNQ that such that when you multiply them from the right by the column vectors, they get to a specific, each vector goes to a specific place, and when you multiply them by the row vectors, each of them goes to some other specified place. So this is a set that's called a K umvirate because there are K constraints. Okay, and here's a lemma. Let's call it global growth. Also good for economic stock. So for an appropriate constant C, and two subsets of SL and Q that are global. So if A and B are global, then, and I need something about the measure. They can't be too tiny, so both of their measures need to be greater than Q to the minus Cn squared. So remember, the size of the whole group is basically Q to the n squared. So this means that their size is at least polynomial in the size of the group. Then, if I multiply A by B, I get almost 99% of the elements in SLNQ. So their sizes can be quite tiny, but when I multiply them together, it's sort of the opposite of the assumption in the Feynman-Ruja. If they're not correlated to a subgroup, their growth is really large. So that's what I claim. This means that under the same conditions, AB times AB, which is AB squared, that already contains all of SL and Q. And this is by elementary reasoning, right? You can get to almost every place with AB. You can also get to every other place with AB inverse, and then you just find a point that's in both. It's easy, yeah.
So if a measure of A and B are not that small, a bit bigger, could you prove is 0.99?
Yes, I will tell you exactly what we get very soon. Okay, so at least this actually gives our main theorem, I don't know where it is, in the case that A and B are global, right? Because, I mean, in the case that A is global, because if A is global, A to the minus 1 is also global, and they have the same measure, and if the measure is greater than that, then the product of A times A minus 1 squared will contain all of SL and Q. And if the measure is smaller than that, then their product will still contain the element 1, but if they are so tiny that they are smaller than that, just the subgroup that contains the element 1 is already of polynomial size compared to the size of the sets. Right, so this gives me the whole theorem for global A and B's. I only need to tell you what to do when they are not global. So how do I get the main theorem if A isn't global? Then I can look at A and A minus 1, maybe they have the correct measure, but I cannot get anything about AB directly from the global growth lemma. So any ideas?
So you descend to this subgroup where they have more density and
Right, so we need to see what, we need to use the definition of what global means. Global means that it's not highly concentrated in anything that looks like a subgroup. If it isn't global, it is concentrated in something that looks like a subgroup. Yeah, so there is a computation here. I'm not sure that I will write it, but I will not go over it. It doesn't really matter. The point is that if A is not global, then there must be a subgroup, or actually a coset of a subgroup, where A is much more concentrated than the original A. So just look inside this coset. Inside this coset, other A just fills the whole coset. That's one option. And then, of course, A times A minus 1 times A times A minus 1 contains the coset. So that's one option. Another option is that A is global inside this coset. And then you just look at, you just restrict to this concept and use the globalist growth. Or A is much more concentrated, but still not global inside this coset, and then you just repeat, you find a smaller coset. The point is that every time you go to a smaller coset, the measure of A grows very rapidly, so you can't go too far with this process. Eventually you stop and you get what you want.
so the only reason you need the A inverse is in the case that it's small? Because this argument will also work with A to the 4.
No, okay, right, so that's a good point. It's a good, fine point. The reason I need A to the minus 1 is because non-globalness doesn't mean that A is dense inside a subgroup. It means that it's dense inside a coset. And then what I can say is that A times A minus 1 is dense inside an actual subgroup, because a coset times its inverse is an actual subgroup. So that's why I need A to the minus 1.
So you said before, can you say again in the global case, what happens if the measure of A is small?
If the measure of A is small, I just say, okay, look at the group of size 1 that just contains the identity element. So the measure of just the identity element is q to the minus n squared, because the size of it, and this is polynomial.
Oh, I see.
In the size of, so this is like it's not an interesting case. You just need to notice that it's not interesting. Okay, so I'll write the words, but you don't have to follow. So if this is write this measure of A like this, and you know that this is greater than q to the minus c n squared, because otherwise there was nothing to prove. And then it's not global, so it has a measure, relative measure, q to the zeta, whatever that is, n times k times the original measure of A inside, ouch, sorry, some good 2k umbrate, and this k, you know that it's not more than t squared over n, because otherwise the relative measure is going to be more than 1, and that can happen, so you don't need to go too far into this umbrate. And this umbrate is maybe G, which is of this form. And then either A is global inside this and you're done, or or it has density 0.99 inside this and you're done, or it's not global inside this and then you just continue. So the idea is, I mean, you have to crunch the numbers, but the idea is quite obvious, and when you actually try to do it, it's also simple linear algebra. So this part is simple. Questions?
Could you talk briefly about what breaks in the abelian case?
About what?
So about this proof, sort of what part of this breaks in the abelian case?
Oh, yeah, yes, I can. None of what I said so far breaks in the abelian case.
Yeah.
The next thing that I'm going to, I mean, okay, just the global growth lemma is just not true in the abelian case. And when I say something about the proof, it will be obvious where I use the non-abelians. At least if I get there, hopefully I will.
So what's left is you're going to convince us that the global growth.
Yeah, so now all that is left is for me to convince you that either the global growth lemma is correct, or that it's not worth the time to argue about it.
What is the symbol there? A has measure q to power some symbol n times k.
Zeta.
Aha, zeta.
It's zeta and it's some constant. I cannot even draw on the board. Okay, so proving how do I prove global growth? I don't really directly prove global growth. I prove a convolution estimate. So you probably have seen this definition before, but I'll define it again. So if I have two functions, it's in SLNQ, from SLNQ to C, then the convolution of f and g is also such a function, and its value at x is defined to be the expectation over a random element y in SL and Q of f of y times g of inverse y x. Yeah, so one thing, there are several things that we need to notice here, but one thing is that this is an expectation over the value of f times the value of g at points whose product is x, of course. And so if the convolution, if it is not 0 at a point x, it means that there are two two elements of the group for which the product is X and where F and G are non-zero. Do you agree? So, and that's why I will use a convolution bound and apply it to the case where F and G are the indicator functions of my sets A and B from the growth lemma. So here is the main lemma. So you have, okay, same as before, A and B as before. F is going to be the indicator of A, G is going to be the indicator of B. And what I want to say is that the convolution of F with G is almost constant. So if I look at the difference between the convolution of F and G and the constant function, which is just the expectation of F times the expectation value of G, I want to say that this is very, very small. So this is smaller than Q to the minus n over 4 times the expectation of F times the expectation of G.
That's an L2 norm.
Sorry?
What's the output?
This is the L2 norm with respect to the uniform measure on the group. Right, so let's see what's going on. F and G are indicator of sets. So the expectation of F is just the measure of the set A, this is the measure of the set B, and this is the function that's just the product of these measures smeared over the whole group. And I say that F convolution G is very close to this. It's close with the factor of Q to the minus n over 4, which means that almost everywhere where this is not zero, which is everywhere, this is also not zero. Which means that almost for every X, there are elements in the group where such that their product is X, and F is not zero there, and G is not zero there. So this is, and so this just says that if I look at all the products of elements from A and B, they cover almost the whole group, and actually they cover almost the whole group almost uniformly. So that's more than enough that I need to prove the global growth.
So do you really need this Q to be N over 4, or can you, the content would be?
I wrote 0.99, so I could write something more ambitious, and then I would need this Q to the minus n over 4. I just don't need it for this particular use. Yeah, so as I said, it's more than enough for what I need. Okay. So any more questions about, so basically I'm going to forget everything and just concentrate on the main lemma from now until the lunch break. So everything clear? Okay, good. Right, so how do you prove such a thing? I don't know how you can prove it, but I can say how we prove it. But for this, I need a crash course on representations for dummies. Not that anyone is a dummy here. So we look, so F and G here, they are elements in L2 of SLN Q, right? They are functions from SLN Q to C. They are actually Boolean valued functions, but generally, this is the set that they belong to. And the group SL and Q actually acts on this L2 of SL and Q. It actually acts squared. It acts in two different ways on the set of functions. So one is where I take a matrix and I apply it to a function by looking at so psi times f at the point x will be just the shift f at psi x. So that's a left shift. If you get a function here, and I apply psi to it, I get another function here. Of course, once I do that, I can also do the other thing, which is shift on the right, except that I want the shift to be multiplicative in the right order, so just for everything to work out, f psi at the point x is actually f at x at the inverse of psi. But this is really a tiny minor thing. And let me tell you why I want to look at these actions, at these shifts. Or can anyone that doesn't know it from before, can you tell me why this is interesting? I mean, I want to analyze convolutions of two functions. So what I want to notice is that the convolution of f and g is a linear, I can write belongs to the span of blah, blah, blah. It's a linear combination of shifts of g. Right? It's expectation of some numbers times g shifted by y to the minus 1. And actually, if I look at it from the other direction, I can say that it's a linear combination of shifts. Actually, shifts from the other side of f. So to understand, it makes sense that to understand convolution, I need to understand shifts. And when you are trying to understand this group, in this case a double group of operators, the thing that is most obvious is to look at invariant spaces. So here's the definition. The definition is that if I have a subspace of L2, so just a bunch of functions that is invariant under right and left shifts. So whenever I take a function from here, shift it to the right, I get something else from here. Shift it to the left, still the same. Then V is called bi-module with respect to SL and Q. And if I have so this is just an invariant space. Of course, I want a small invariant spaces if I can get them. So if any invariant space that is contained in V must actually be the empty space, then V is the smallest one that I can say, I can get, then V is called irreducible. Okay, so I don't have much time for the talk, but this is the first time that I reached the point where I use the non-abelianness. Because if the group had the group been abelian, all the irreducible bimodules would just be the eigenfunctions of the shifts. So these are just the Fourier characters, and they are all of dimension 1. Because SLNQ is very far from being abelian, I get subspaces of large dimensions. So there is this Peter Weil theorem which says that you can partition the whole space into such irreducible bimodules. So the whole space is just a direct sum over some set of indices where each W rho is an irreducible bimodule. They are all orthogonal to each other, so that's very nice, which means that for every f, there exists a unique way to write f as a sum over these indices rho, of the projection of f to W rho, which I write like this. So, and it turns out that when I look at the convolution of f with g, okay, I will say it in a way that maybe you cannot follow, but you can then think about it and understand. If G belongs to an invariant space, then of course all of its shifts are inside the invariant space. So if G is an invariant space, convolution with any function is in that invariant space. And also same for f, just from the other direction. So if G is in one invariant space and f is in another, then the convolution is in both the spaces, but they are orthogonal. So actually, this thing just completely partitions into invariant spaces. So the convolution is just the sum over all irreducible spaces of the convolution of this times the times that. Right. So to understand the convolution, all I need is to look at this. Okay, and I have time to say a little bit more. So there is one irreducible space that's always there, and you can even see what it is, even if you don't know this from before. What is the most simple invariant space inside L2 of SLNQ? Constant functions. Constant functions are, of course, invariant. So I can write this as f equal const, convolution with g equal const, plus the sum over all the rest. And f, the projection of f equal const is just the expectation of f. Right, it's the projection on a space of dimension 1, it's the inner product between f and the constant 1 function, which is just the expectation. So these are just, I just held the product of the two expectations. And so if I want to say that f convolution g is very close to the product of the expectations, all I need is to bound this. And because of the time constraints, I will say only a little bit about how it works. It will be in a story form. Okay, so here is something standard. Yeah, so I want to look at the sum over all row except the non-constant one of this thing. So I want to bound the norm of this thing, and I can write it. I can use the triangle inequality and bound the sum of the norms.
Square. Sum of the norms squared? You want the
This time it doesn't matter. I can do the sum of the norms squared, but other powers are up to a constant times n. It doesn't matter really. But yeah, if you feel comfortable, just add a square here. But here is the point. First of all, I think of the convolution as an operator acting on G. So so there's an operator that corresponds to F equals rho, and the way that it acts on G is by convoluting with F. And then I can upper bound that by the operator norm of this times the 2 norm of G. This is the operator norm from L2 to L2.
Would you think of this operator as the full convolution of f with g, or just the convolution of the row part of f with g?
Just the convolution of the row part of F. That's why I worked
Because
to
your formula doesn't have.
what formula?
Just write an equals row.
notation.
Oh, sorry. Yeah. Why did I put row here if not to use it here? Yeah. Sorry. Okay, and this is a trick by Sarnak and Zhu, which is very simple, but I don't have time to show it. They know how to bound this operator norm. It's actually the regular. It's just the L2 norm of F equals rho multiplied by something, or actually divided by something. So the operator norm is the norm of F. It's bounded by the norm of F divided by the dimension of the invariant space that F belongs to, actually to the power 1/4 for some reason. Doesn't really matter. The point is that if I knew that all the dimensions are large, which here is a big use of non-abelianness, then I could say that this is small. I could use Cauchy-Schwarz and bound it by the norm of F, by the second 2 norm of F times the 2 norm of G, which is the same as the measure of A times the measure of B. So this is if I knew that the dimensions are small. If the dimensions were large. So the only problem is that it's not true. Some dimensions are small, some dimensions are large. So the Sarnak-Zhu trick doesn't work by itself. And with 2 minutes that I have, I can tell you more or less how to continue from that. What we say is the following. We have first we define levels. So not all rows are the same. Different rows have different levels, which is related to their tensor rank. And we show that if the level is high, then the dimension is also high, and so this is small. So all that we are left with is to deal with the rows which have small level. And the next thing that we show is that if F is global and the level and D is small, then the projection of f, the projection, I don't know, of f on the set, on the sum of all W rho where the level of rho is smaller than D, this is small. I have global and Boolean. I'll say it again because the board is already too much of a mess. So the point is that for the rows where this dimension is large, I'm fine. For the rows where this dimension is not large, I can look at the space of all the W's whose level is small. And a general F can have, it can belong to this space. But a Boolean valued function F that is also global, it cannot have a large weight on this. So the denominator will not be so large, but this and this are going to be very small. So the whole sum is, so this is a win-win situation. Either this is small or this is large.
So it's enough for one of the functions to be global.
It's actually enough for one of them to be global, I think, yeah.
Is it the last thing? Is it like philosophically hyper-contractive?
Yeah, so, yeah, okay. So I want to say some names, and of course I can't say them without my notes. And also, okay, this is good, I remember. Gurevich and Howe defined these levels. You would think this is like representation theory. It exists from 18-something. You would think that this is a result from maybe the early 1900s. This is a result from 2020. They defined these levels, and in 2021, Guralnik, Larsen, and Tiepp showed that if the level is high, then the dimension of this is also high. So all of this is preterist. No, all we need to do is use existing results, but they are existing from the last few years, and then and to get the D-level inequality to prove that this projection is small if f is Boolean and global. This we do by a reduction to the case of abelian matrices. And the case for abelian matrices was proven by me and Ellis and Noam Lifshitz maybe 2 years ago. And the problem is that all these levels, they depend on a representation theory of non-abelian groups. It doesn't seem like you would be able to use something about the linear group. But it turns out that somehow the definitions of level somehow match. And also, SLNQ is embedded inside the abelian group, and it consists of a large enough portion of it that you can just take functions on SLNQ and extend them over the linear group and just use the existing results. So all that is left is just to make the right definitions and use existing results. That's it.
Okay, so let's thank the speaker.